Progress, History, and Finality, War and Space. Hello and welcome. I just want to set a couple of ground rules. You're definitely going to hear some pages turning today because I'm reading from a script, as I often am. You may hear some snoring cat noises because the cat is next to me. And I think those are the ground rules. Just expect those two things. All right. In the last lecture, I framed the lives of some important scientists through the lens of large families and of maternal mortality. In the 19th and early 20th centuries, those two ubiquitous elements shaped the way many people lived and what expectations they had about the possibilities of life. They helped each other, they competed for resources, and not everyone could get an education, and they were likely to lose someone, a parent or sibling, as they grew up. As I told you last week, we're coming to the present. We're pulling the threads of the past into the web of the present, into the way that we all live now. In some ways, science and especially technology are so present they are invisible. In other ways, they're at the forefront, especially when we are acutely aware that we are living lives in a new way or in a changed way. As a kind of intellectual game, I collect experiences that previous generations could not have had. Now, having emerged from the pandemic, we all share the experience with those who've lived through plagues of the past. But we have pulled all of our connection and communication technologies to the forefront during that. And that, no one before us ever shared. Just to explain this idea a little further in the context of scientific disciplines, I was listening to a podcast last year, and the speaker, Thomas Friedman, was talking about COVID-19 and the way that people were suddenly aware of the power of nature. And he said, well, Mother Nature is just chemistry, biology, and physics. So I was brushing my hair and I was getting ready for a Zoom call, and I stopped and I thought, that sentence and the thoughts in that sentence weren't even possible for much of the history of science, because biology, chemistry, and physics have roots in studies that were done by a variety of scholars and experimenters and builders. But all these fields didn't exist really until the 20th century. That's when they come into focus as separate fields. And it is now, through the frame of these different fields expressed as business and national interests, that the problems and promises of science are shown. The tools and methods early adopted by the Royal Societies of France, England, and the labs and schools in Germany were taken to the common folk by means of public shows. The Magdeburg Hemisphere experiment with horses, which demonstrated the pressure of atmosphere. The electricians, like Francis Hauksbee, created sensations and lights. There were traveling scientists who demonstrated vacuums and worked with air pumps. And you saw that in the painting by Joseph Wright of Derby in the first lecture of this course. In fact, that's not so different from today. YouTube is filled with science experiments you can do or think about, and there are great biology shows with the Body World and Jurassic Quest. I have a couple of links in the notes on that. Science retains its character of marvelous entertainment. But Perkins' mauve is in some ways the way forward. He monetized his invention. He built a factory. He sold a lot of purple dye. And that pathway has become one of the pathways between science and social structure. Take a quick look at the Wyss Institute. Look at how their website explicitly describes discovery to making money. They are built on foundations of, well, we can say purple. And mauve isn't the only example of a way forward. We see that science becomes inextricably imbued, and imbued is a word here, with national interests. It becomes extremely important for nation states to have a research program. The fields of biology, chemistry, and physics are so natural to us that we have standards for K-12 curricula, and we blame the government or the local school district for falling down on science education. We have structured education in society so that they are important fields of study right through the postdoctoral level. And they've become so specialized that it is a surprise if someone has a deep knowledge in more than one of these fields. Our nation, like other nations, competes to fund and retain top physicists, chemists, and biologists. So you see the reference to the Wyss Institute, and I want you to make explicit in your mind the link between invention and monetization. I reminded you about the National Academy of Sciences established in America to help the war effort. The Gatling gun, an invention of the American Civil War, allows a continuous stream of bullets to be pumped out across a battlefield, as I mentioned, and its inventor, Dr. Richard Gatling, apparently thought it would reduce the size of armies and show the futility of war. And then I also showed you the explosion caused by Fat Man over Nagasaki in 1945. These are definite philosophical failures on all fronts. And maybe the foundation of the National Academy of Sciences in 1863 in America ought to be connected to the little moment I mentioned in the harbor at Shanghai. At least I think I mentioned this. If not, I want to put it in front of you here. This is related in a book of collected letters by the English art critic John Ruskin. And it's a guy looking at the technology of China, and he's saying he doesn't think really that religion is a good way of changing people's minds. He thinks rather technology would do it, and he says, let us get at them with this sort of article, and steam at 60 pounds on the square inch. That would do it. That's the thing to civilize them. 60 pounds on the square inch. The self-opinion of citizens and their respective countries were tied to scientific progress, and this little quote shows that. The founding of national or royal societies dedicated to the scientific endeavor, which was the province of the few, became the identity of the average upper middle class, increasingly educated citizen. This was a significant moment, a seed from which a great change grew. Now, it's fair to say that America and Britain dominated the development of science in the 19th and 20th centuries in the context of being a nation state, and the shape of our world and what we believe civilization to be is founded in the definitions of what science can and should do for us. We tied progress to science from the 1870s to the 1970s, when a counterculture stream against science started to grow up. Well, it's equally fair to say that the locus of power is currently shifting to companies with no particular national loyalty, and the definition of civilized is up for grabs. Our national abilities and inabilities to respond to things like a pandemic gave us a kind of funhouse mirror of civilization. I showed you this in the previous lecture. This is an image of what electricity means to the whole world: economic development, the cloud, connection, education, health, and travel. I said that prehistoric cave art was evidence of all we needed to do in science, meaning everything that was important for science was present in prehistory before even the advent of writing. Problems, tools, close observation over time, and organizing ideas were there in these tantalizing forms. The control of water, other forms of energy to do work for us, is another essential. Those have been with us certainly since 2000 BCE and probably well before. But there are exponential shifts that occur after 1700, when the Industrial Revolution and a population explosion together produce not necessarily misery, but surely to goodness, not peace and not equity in the world. Now, maybe because we Americans love scrappy bootstrappers, that's our national identity, our science biographies are littered with stories of people who lifted themselves out of exclusion or poverty or disability or ignorance, and I am myself a fan of those stories. Just as I won't be talked out of God or a soul, so too I won't be talked out of villains or heroes, people lifting themselves up. But they all have a context. In the next 4 stories, the power grid, the atom, the green revolution, and the space race, I'm going to sketch out a little of each and explain that context travels through and beyond nations. So the big ideas for this week are 2 big ideas. One comes from my youth, the science fiction Terminator series, No Fate But What We Make. And the second is a reversal of thought from the first half of the course. Science now generates a great sink of wealth. As we look at the future of the electric grid, the understanding of the atom, the production of food, and the race into space, we'll ask ourselves, what kind of fate are we making? And we'll consider again how wealth follows science. This is a favorite image of mine. It features Nikola Tesla in his Colorado Springs lab. He is the holder of a number of patents in electric generation and wireless control and communication. And he's sitting next to a Tesla coil, which was a high-frequency, high-voltage transformer. He loved doing dangerous-looking stunts, usually with electricity, and all successfully. He lived to a ripe old age. Despite his intellectual abilities and ambitions and fame, his story is a sad and strange one. He was born in Croatia in 1856 and went to engineering school and worked for the Continental Edison Company in France. he emigrated to the U.S. in 1884, apparently lost all he had on the journey, and arrived in the U.S. with 4 cents in his pockets. But, buoyed by a letter of introduction, he worked for Edison as his first job in the U.S. He was 28. He knew about the relative advantages of AC, and he hoped Edison's company would adopt it. When they did not, he was disappointed, and he chose to move on. He took on menial jobs, including ditch digging, but not for long. He registered a patent on arc lamps and then registered a business, his business, in 1885. That's just a year after he arrived in the U.S. In 1887, he founded the Tesla Electric Company and began to work on an AC current induction motor. Even though he left the Edison Company, he and Edison continued to correspond, and at one point in the 1890s, they were talking about radium, polonium, and X-rays. The circle of people doing science, interested in science, had become a network of professional societies, labs, companies, and universities. American labs, for instance, were keeping in touch with French developmental research. So in that discussion, while interested, Edison had had some medical issues because of radiation, and one of his lab assistants had died. So Edison saw radiation as a dangerous field of research, and in the letter he sent to Tesla as part of this conversation, he said that he would refuse to have anything to do with it. Edison and Tesla did have some rivalry. We'll talk about that in a second, because Tesla partnered with George Westinghouse in order to light the Columbian Exposition of 1893. The Columbian Exposition was a landmark event. It inspired authors like L. Frank Baum, who modeled the Emerald City in The Wizard of Oz after the White City of the Exposition, which was built for the Exposition. It also inspired one of the verses in America the Beautiful. If you'd like to see a little more, I've put a link in the notes. Tesla was in some ways unfortunate and very fortunate in his partners. When he was in need of cash, George Westinghouse bought his patents for $60,000. So he got the help he needed, but he never made the fortune he could have made from his inventions. And when he grew old, he became markedly strange and even delusional, and unable to pay his bills or keep himself. So Westinghouse, the company, quietly paid for his hotel room in New York and saw to it that he was never homeless. Many of Tesla's inventions, particularly his wireless control devices, waited for another day to be fully developed. But what you should know is that electromagnetic induction, which had fascinated a lot of the best mathematical minds in science since the 1830s, like Michael Faraday and James Maxwell in particular, also fascinated businessmen and people like Tesla, who tried to work out motors, power systems, and eventually monetize grids of power and all the pieces, which they also tried to own, then went into grids. For instance, the light bulbs in this picture were invented just 6 months before the fair because of a patent infringement suit by Edison. Westinghouse had to build new kinds of bulbs to connect to Tesla's incredible generators. Tesla was someone who didn't manage to monetize his ideas. He didn't manage to create a grid of customers, a set of standardized parts, and connected energy generating stations. George Westinghouse, by contrast, did those very things. Westinghouse managed to do those very things 3 times over, first with railroads, second with gas, and then again, third with electricity. So, how does something like a grid, something we all live within, get started? These 2 inventors, in contrast to Tesla, did manage to create systems to hold their ideas and to generate money. Electricity was an invention, it was a race, and it was a business venture, all of which became a matter of national policy and safety. And that is what science looks like in the 20th century and the 21st century. So Westinghouse, he was self-made. He took out patents starting at the age of 15. Then he served in the American Civil War. He invented the air brake for the train, building up his fortune. He found natural gas on his own property, and then he invested in electricity with the patents he bought from Tesla. He won the War of the Currents in 1893 by lighting up the World's Fair and by building a power plant on Niagara Falls, which we'll see in the next slide. Edison gained his early fame with the phonograph, film, and the light bulb. He built a power station using direct current and attempted rather ruthlessly to persuade the country that Tesla's alternating current was dangerous, going so far as to electrocute an elephant and then a condemned prisoner as a way to make that demonstration about the dangerousness of DC. or of AC. So, but he lost the War of the Currents because the plant that Westinghouse built at Niagara Falls sent power to Buffalo, New York, and that output and that range dwarfed the Pearl Street station that Edison had built in New York, supplying just a small 2-block radius of customers. Despite having the better system, Westinghouse lost his company in the panic of 1907. He had too much debt, and his loans were called in. He was bought out by J.P. Morgan, who was an investor in Edison's inventions. That said, we do continue to use the AC, which was favored by Westinghouse, because it does actually allow generation of power to be transmitted long distances and to be transmitted safely. Westinghouse has a character that's worth pausing to consider. He came from a supportive family. He was creative himself. He was a problem-focused guy, and he stood ready to patent any of his good ideas and to make money from them. He became immensely rich, but despite living in the days of robber barons, when to be immensely rich was to be reviled, he was really not a social monster. Instead, he was apparently a really good employer and a decent guy. He promoted the idea of the weekend by giving his people a half day on Saturday and Sunday. He and Norman Borlaug, whom we will look at in the next section, seemed actually to just want to do something good for the world they lived in. So in a previous lecture, I stood on my soapbox to say that climate change is about accepting responsibility for known problems and also about taking responsibility for the effect of unintended consequences in technology on the most vulnerable people. No one meant to wreck someone else's life, but it happens. What will we do? Another way of saying this is what I said: the poor are the least able to deal with floods, droughts, tsunamis, earthquakes, with the short-term effects of climate change, and the nations who can help, should step up with good policies and remediation. So I said that in a previous lecture. Here I'm saying it's possible to be a good employer and a good entrepreneur. Nothing about how corporations work is inevitable or unavoidable. No one has to oppress their employees. I've put a few links in the notes for this story about Westinghouse. On the right below is Niagara Station, and on the left is a wind farm in Hainan, China. And there's a little grid there of the smart power grid, an image of it. So what are the most significant changes that are going to happen in your lifetime? I think certainly energy is going to be one of those significant changes. How we live now and how we will live in the future will certainly change. I also think that climate change and the dependency on oil is going to be intertwined, and we will have to solve it. But this is part of the future that energy points us toward. All right, let's tackle another part of our story, and this is a related part, but going forward, what's in an atom? Our current understanding of what's in an atom is really still developing. As you recall, the nature of the atom was a question opened up by the Greeks, tackled again by the alchemists, and yet again by the chemists, and in the 20th century by the physicists. The model of the atom here in this picture is the one that many of us learn, although it's not really what scientists think is happening. It's just a handy image. In Greek thought, the atom was the smallest indivisible unit of which all things are made, and it became, in the teachings of Aristotle in the 3rd century, 4 elements: earth, water, air, and fire. And you may recall that Alexander the Great was tutored by Aristotle, which is not bad. Anyway, this concept of earth, air, water, and fire hung on for a long, long time because it more or less worked and it conformed to the world as we experienced it. Now, for alchemists, understanding the elements became in part a search for ways to extract valuable metals or to create them. The Germans and the Spanish, for instance, both developed skills in mining and metal extraction because they both had access to gold and silver mines in the territories that they held, particularly in the New World, but also in Europe. Knowledge of the elements were also used to generate weapons of war. For instance, Greek fire was a kind of flame-throwing weapon used by one ship against another, even in the 6th century AD. Its exact recipe has been lost. But alchemy and weaponry went hand in hand right up through the Renaissance, if you remember the letter of Leonardo da Vinci. So reassessing the fundamental elements was part of the program, if one could call it a program, of the Royal Society. They wanted to understand what's in air, how it works, what does burning actually do, what's in a vacuum. These were the subjects we covered when we looked at oxygen. So now, what's in an atom? Going forward, Now you can kind of find, and this is a picture of one of these cheat sheet, how to understand the history of the atom. These are all over the place. You can buy these in the bookstore, or you can buy these online. So what's in an atom? The story has a very standard way of going forward. First, John Dalton. He was a Quaker who came from a weaving family. He went to a dissenting school, and he was not allowed to be in a regular school because of his religious beliefs. He taught math and natural philosophy at a college-level institution for dissenters in Manchester. Then he was invited to become a member of the Manchester Literary and Philosophical Society, which was his step into the wider community of those interested in science. He maintained a fair degree of independence as a researcher and a writer, but he was elected to the Royal Society when he was 56. He published on a number of subjects, including grammar and meteorology. There again, he was living in the days before specialization. So relevant to our story is this. Around 1805, he put into print the idea that atoms of the same element will have the same weight. For instance, one oxygen atom is going to be the same weight as another oxygen atom. Atoms of different elements combine in fixed and predictable ratios to create chemical compounds. From then and there, the story keeps going. Then we have J.J. Thomson, who used cathode rays to interact with electric and magnetic fields of elements. He proposed that there are small, light, negatively charged electrons with some positive matter, basically within some kind of positive matter, basically what we call the plum pudding model. You see that there. Ernest Rutherford, who was one of 12 siblings, came to England from New Zealand, and then he went on to Canada. He showed that the nucleus was small and that electrons were separable from the nucleus. Niels Bohr, a Dane, showed that electrons were negatively charged and changed those charges in a kind of step order, and you can see the planetary model there. Then the German Erwin Schrödinger and Werner Heisenberg followed. They made modifications to the idea about where electrons might be mathematically, and James Chadwick discovered neutrons. So this is a series of visuals about the story of the atom that I think are helpful to understand our development of it, our development of our understanding of it. And you can really find a lot of these online, as I said. Well, what about applications of the model? You recall that Marie Curie said that she was working with the chemistry of the imponderable. What they were measuring experimentally was very different and required a very different set of tools for looking. Radioactivity was a new kind of essential chemical and physical quality to measure. Now, among the unstable radioactive elements, uranium-238 is what we find in most of the world. Well, technically, we don't find it. It's hard to isolate from the soil, rocks, and water in which it's found. Radioactive means that an element gives off particles from its nucleus. A nucleus is unstable when it has an imbalance between neutrons and protons. It then ejects particles and releases energy in order to become stable again. Before World War II, Lise Meitner and Otto Frisch, aunt and nephew, both scientists, were working in Germany on bombarding the nuclei of uranium. They realized that they could theoretically split the nucleus or create a nuclear fission. And having explained in a paper published in Nature in January of 1939 how it might happen, Lise Meitner dropped out of the work, not being interested in where she knew the research was leading, into developing weapons. But, with or without her, the work was carried on in America and in Germany. As you know, the Manhattan Project was begun in order to make the idea of splitting an atom into a practical weapon, an atom bomb. The trick was to create enough U-235, which was the isotope of uranium most likely to produce an explosive and ongoing nuclear fission. If you want to follow it in detail, I've included a link to an entertaining and interesting site, and you can also view the Trinity test there. I'm quoting Robert Oppenheimer, one of the senior scientists, who said this in his memoirs. "We knew the world would not be the same. A few people laughed. A few people cried. Most people were silent. I remembered the line from the Hindu scripture, the Bhagavad Gita. Vishnu is trying to persuade the prince that he should do his duty, and to impress him, takes on his multi-armed form and says, 'Now I am become death, the destroyer of worlds.' I suppose we all thought that, one way or the other." So here is the practical application of the story of the atom. And what a sorry end to this research. In historical context, the total destruction of Hiroshima and Nagasaki were believed to be necessary by the U.S. military. Writers at the time said that military leaders were convinced that the Japanese, fighting in their own country and for their own homes, were willing to resist to the last person. Something as violent as a nuclear bomb, something that shocked them and convinced their leadership that they could not win, was believed to be a way to save both American and Japanese lives. Historians have been divided ever since on whether or not that belief about Japanese character was the real reason that bombs were dropped, or was it merely to bring an experiment to its natural conclusion. It's impossible to know now. You can only look backward. Nuclear power has been reviled for its potential and actual dangers, and also become the poster child for the NIMBY movement. NIMBY stands for Not in My Backyard. But nuclear power has also been harnessed for, you could say, the purposes of peace. And they were in fact called that, atoms for peace, at one point after the World War II and during the Cold War. So what to say about the future of nuclear energy? It's part of the questions about the energy grid that I raised earlier. The big dream that everyone is chasing is nuclear fusion rather than nuclear fission. Current predictions are around 2030, but every so often a company announces that they have another piece worked out, and I've got a link in the notes for that. The 20-year-old fusion energy technology developer TAE Technologies has said that its reactors could be operating at commercial scale by the end of the decade, thanks to a newfound ability to produce stable plasma at temperatures over 50 million degrees, which is nearly twice as hot as the sun. It's kind of mind-boggling. And it says, with these milestones behind it, TAE was able to raise an additional $280 million in financing, bringing up its total to $880 million and making it one of the best-financed private nuclear fusion endeavors in the world. To get to this point, the company spent over $150 million on prototype machines, so it is a literal sink of wealth. Well, locals are worried about the storage of nuclear waste and the potential of a disaster like Chernobyl or TMI in their locale. Curiously enough, no one has been really too upset to have a giant particle accelerator or collider in their backyard, except those who have to pay for it. So as we move forward, keep in mind that atomic research carries the weight of permanence and magnitude and potential and alters the quality of life. Truly, it is significant. Continuing with the atom. Scientists are working pretty darn diligently to figure out what's going on at the subatomic level. There's currently what's called the Standard Model, developed in the 1970s and refined constantly since then, which explains the kinds of subatomic particles and how they interact with each other. So I'm going to be quoting pretty closely the U.S. Department of Energy website, and the image from that website is on the right, is located there. The interactions of quarks and leptons and bosons and Higgs bosons particles explains and predicts 3 of the basic forces in the universe pretty well. First, electromagnetism, the forces that create electric and magnetic fields. The field and theory of electromagnetism describes how light travels and how chemistry happens. Second, there is the strong force that binds atomic nuclei together. Third, there is the weak force, which explains how nuclei decay. And the Standard Model does not explain gravity, nor does it explain what dark matter is, and what many physicists suppose makes up the universe is dark matter. So I'm going to quote directly from that website here, because I think it's pretty helpful. The Standard Model explains 3 of the 4 fundamental forces that govern the universe: electromagnetism, the strong force, and the weak force. Electromagnetism is carried by photons and involves the interaction of electric fields and magnetic fields. The strong force, which is carried by gluons, binds together the atomic nuclei to make them stable. The weak force, carried by W and Z bosons, carries nuclear reactions that have powered our sun and other stars for billions of years. The 4th fundamental force is gravity, which is not adequately explained by the Standard Model. And as we said, physicists understand that about 95% of the universe is not made of ordinary matter as we know it. Instead, much of the universe consists of dark matter and dark energy that do not fit into the standard model. Now recently, scientists announced that they thought they had an anomalous result. A particle, called a muon, was not behaving as it was supposed to be behaving. Now instead of being worried or upset about that, they were delighted because they're actively trying to either shore up or break apart the ideas about what these most fundamental particles are. And I've put a few links to that moment in scientific discovery. So one practical application of research on the atom is energy. Another practical application is computing, and really everything else is up for grabs. What will be the most significant change in your lifetime, and how will you recognize it when it comes along? I have a pretty strong feeling that theories about subatomic particles and the forces of the universe are going to change and are going to continue to be developed. And if you're interested in following that, I've put in a link to CERN and to Fermi, two labs that are continuing this kind of research, and I think are pretty interesting. Aside from developments in the understanding of the atom and the Cold War, a very different set of stories can be told of the efforts of the 1960s. As a historian, I'm willing to take the minority position and say that one person can make a difference. It helps, of course, if other people come alongside to contribute. But Norman Borlaug's life seems to exemplify what happens with someone with a burning drive to fix something, fixes it. The results of the Green Revolution are both positive and negative, as we will see in this lecture and the next. But Borlaug is the center of the Green Revolution and the end of the need for worldwide famine. Borlaug was born in the early part of the 20th century and grew up in a rural farm family in Iowa. He worked his way through agricultural studies in college, and he saw hunger and hardship firsthand during the Great Depression. As he finished up his bachelor's degree, he became interested in plant pathology, particularly the rust fungus that kills food crops, and he made that the focus of his further study. His lab in Delaware, where he went after securing his PhD, was seconded to the war effort in the 1940s. But following that time, he joined a project to help Mexico increase its wheat yield. Through grit and attention to breeding work, he succeeded in developing a semi-dwarf wheat resistant to pathogens. And I've put a few links to that information in the notes. He shared that wheat with the whole world, but particularly the US, Mexico, India, and Pakistan. Famine as a regular occurrence ceased. Although he is relatively unknown, Borlaug won the Nobel Prize, and he is credited with saving at least 1 billion people from starvation. Famine is now more or less generated purely by politics. There is enough food being grown to feed everyone. In a sense, this is a story about basic science, the science of breeding, being applied to a simple problem, hunger, and succeeding. We'll look at a young scientist and an activist, Boyan Slat, next week to think about another such approach to the problem of plastic pollution. No story in science and society has just one end. The countries which more than doubled their production, India, Pakistan, and Mexico, have had to adjust their indigenous and local methods of farming to American-style methods of large-scale farming and crops developed elsewhere. Larger scale of necessity brings larger problems. Many smaller farmers get squeezed out, and having fewer varieties of wheat means that the existing wheat is vulnerable to new pests and new pathogens. These are concerns that any national program has to consider, and concerns that they have to enact and solve at the local level. You can consider here a historical food catastrophe, the Irish potato famine. It happened in part because there was a single kind of potato being grown. There are hundreds of kinds that originally and still are grown in South America, but by the 1850s, Ireland had focused in on one potato stock that grew easily in poor soil and provided a lot of carbohydrates for people who were absolutely depending on it. Being overrun by a war or having bad weather are significant problems, but a plant blight combined with either of the other two is catastrophic. And that's what happened for the Irish. Just such concerns are voiced by people who watch the big agricultural firms like Monsanto distribute seeds and pesticides. Who owns the variety of plants that they breed and distribute if they get out of the hands of the farmers to whom they are sold? Do we even have options to abandon pesticides and feed the world? Then, how much of nature is owned and can be controlled? And what about unintended consequences? If something gets out, so to speak, whose job is it to fix it? Whose fault is it, and what are we going to do about it, are the kinds of questions we didn't really ask until about the turn of the 20th century. Once we saw that we could truly affect the environment quickly, we were not only solving problems like staying warm and eating enough and having enough stuff, but we were also causing ourselves problems in the pursuit of these things. Then it was possible to perceive our needs as problems. Until that point, the only problem was not staying warm or not having enough to eat or not having enough material goods. Now, having solved those problems became problems. I'm sharing here the work of a photographer, Luca Locatelli, whom I follow on Instagram. This is his work for a recent National Geographic article on the circular economy. His photography features a company in New Jersey here called AeroFarms. I'm wondering if you think this kind of farming can make a dent in the way we process food, and can we do so sustainably, both locally and for the whole world? Next week, we will step back and bring in the thread of computing. It's a little odd to tell the story of the space race without the story of computing, but I'd like to keep the focus on the 1960s, and so we'll stick just with the Cold War and this particular event. In the 1960s, the backdrop to almost all scientific endeavors was physics and the race to dominate weapons production. A mutually assured destruction policy was an actual political approach to the nuclear arms race. In the lecture about Darwin, I included the picture of Charlton Heston breaking down on the beach at the end of Planet of the Apes because I was thinking about how we discover and rediscover who we are and where we are. That discovery can be done with joy or with despair. The strange consequence of attempting to dominate space was that we spooked ourselves off the planet, so to speak. When Sputnik was launched in 1957, Americans panicked. Russia was ahead. It was winning the war. It had better mathematicians and physicists, and who knew what that satellite was capable of seeing or doing? Fear spurred our space program ahead. I can't do justice here to the depth and breadth of the American space program, but I think I can say that the Americans who watched the Apollo missions watched them with stars in their eyes. They loved the thought of brave men, and it was men, brave, skilled pilots and scientists risking their lives to get to another planet. I'm going to read the 4 goals on the Apollo mission webpage. Establishing the technology to meet other national interests in space. Achieving preeminence in space for the United States. Carrying out a program of scientific exploration of the moon. Developing human capability to work in the lunar environment. The blend of technology, science, and national interests and human interests couldn't be any clearer. As regards technology, miniaturization of machinery, computing for trajectory and precision, climate control, lifting power, those were all necessary elements. And all of those efforts paid off in the future in things like hearing aids, deep diving equipment, and drones flowed by GPS. What's on the moon, and looking at it more closely in person, is the point of, well, curiosity. You can say that we've done just fine without knowing for at least all of recorded human history what's on the moon. But, of course, we're all glad that we went. After a series of dress rehearsals and some disasters, Apollo 11, with Buzz Aldrin, Neil Armstrong, and Michael Collins, landed on the moon. Again, I'm going to quote the NASA website that gives an overview of the Apollo 11 mission. It's kind of weird the way it's phrased, and it's incredibly dry, but even through this kind of weird science speak, it still makes you catch your breath thinking about what could have gone wrong. Armstrong and Aldrin spent 21 hours, 36 minutes on the moon's surface. After a rest period that included 7 hours of sleep, the ascent stage engine fired at 124 hours, 22 minutes. It was shut down 435 seconds later when the Eagle reached an initial orbit of 11 by 55 miles above the moon, and when Columbia was on its 25th revolution. As the ascent stage reached Apollon at 125 hours 19 minutes, the Reaction Control System, or RCS, fired so as to nearly circularize the Eagle orbit at about 56 miles, some 13 miles below and slightly behind the Columbia. Subsequent firings of the LMRCS changed the orbit to 57 by 72 miles. Docking with Columbia occurred on the CSM's 27th revolution at 128 hours 3 minutes into the mission. Armstrong and Aldrin returned to the CMS with Collins. 4 hours later, the LM jettisoned and remained in lunar orbit. So there you have it. As I said, a little bit weird and a little bit dry, but that is how it's described. I'm including in this week's clips an unmistakably patriotic version of the moon landing produced by CBS. In an important sense, this is a story that would not be told by a major media corporation in this way anymore. It defines science and achievement with pride in human and American abilities. My parents called me in to watch the moon landing. I was 3. I barely remember anything, but I'm proud to say that I saw it. Apollo 17 was the last mission to the moon in 1972. We want to get back out there, right? Now it's a couple of billionaires who've got their money from something other than a nation state that are thinking about funding it. The space race is a great case study for historiography. Historiography is the study of how we tell ourselves history. So I grew up with the America First story, but Hidden Figures, the book published in 2016 and produced as a movie in that same year, is a reframing of the story of the moonwalk through the eyes of the support team, the people who made it possible, the African American women computers. Katherine Johnson, Dorothy Vaughan, Mary Jackson, and Christine Darden have been honored for their work in breaking barriers and in supporting NASA's missions. In the same way that the story of the moonwalk couldn't be told by a major media corporation the way CBS told it then, so too the story of scientific achievement is really told differently now. Hidden Figures looks again at how and why science works, and who gets credit for achievements. We've come to value diversity as contributing to courage and success, and now we expect to look for diversity in the way we conduct and consider science experiments with the body, with the environment, and with international projects like the International Space Station. One of the most interesting and practical outcomes of rocketry and spaceflight has been the addition of satellites to our information systems. We use satellites for communication and location as easily as we once used maps and letters, mathematics and timepieces, and radio signals for our longitude and latitude. Now we are using satellites. But these are efforts by private companies like SpaceX rather than nations. And so we are cheering these national efforts through NASA, but we're also dependent on private companies. And that makes the future an interesting place and somewhat uncertain. And on that note, I'll end. Our last lecture will focus on the future of DNA, the Big Bang, computing, and climate change.